Hello, I'm Anand Jain from Hanumangarh, Rajasthan. I welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subject. Today in our class 12th physics, in our chapter electric circuit, we'll study simplification of series parallel circuits, and in this introductory video in next 12-13 minutes we will understand what is series circuit, what is parallel circuit, how their equivalent resistance is obtained, and we'll also solve three very simple series parallel circuits. Let's first explain what is series connection of resistor. If several resistors are connected in a group such that the second end of one resistor is connected to first end of another resistor and so on, then this combination is called as series connection. Now layout of three resistor in this yellow highlight circuit and in this unhighlighted circuit looks very different, but both represent series connection of resistor, as 3 ohm got two terminal A and B and the second terminal B is connected to one terminal of 2 ohm and another terminal of 2 ohm is connected to one terminal of 4 ohm, and finally circuit got its connection from first terminal of first resistor and end terminal of last resistor between A and D, and between A and D this yellow highlight circuit and this blue frame circuit are identical in behavior. In series connection, all resistors have the same single current flow path, so they have identical amount of current in every one, and the total voltage which is applied across this combination as across A and D get divided among series connected resistors, as here the total voltage of A and D get divided in 3 ohm, 2 ohm and 4 ohm. Here three resistors R1, R2 and R3 in a series combination are connected to a source of V volt, the voltage of which is measured by this voltmeter, and ammeter is also connected in the circuit to measure the circuit current, and let it is I, and 3 voltmeter measure respectively voltage across R1 as V1, across R2 as V2 and across R3 as V3. Then as per Ohm's law, since current in all three resistance is same as that of total current, so voltage across R1 is V1 is equal to IR1. Similarly, V2 is IR2 and V3 is IR3. The total applied voltage across this combination of three resistors at N terminal P and Q, that is V, got divided among three resistors as V1, V2, V3, and sum of three voltage V1, V2, V3 is total applied voltage. And if we substitute the value of V1, V2, V3 in terms of circuit current I and respective resistance, then V1 is equal to IR1, V2 is IR2, V3 is IR3, and when this identical current of series circuit is brought as common, we can say the total applied voltage in terms of circuit current got this relation. Now this series combination is replaced by a single equivalent resistance R series. Then across P and Q with the same voltage, same I current will flow in the circuit, and Ohm's law for this single resistance can be stated as V is equal to I R series equivalent. And if we compare these two relations, we can say the series equivalent resistance is sum of individual resistance. So in series connection of resistors, if we have to replace several resistors by single resistance, then that single resistance is equal to sum of individual resistances, and this will help us to use Ohm's law, as this Ohm's law V is equal to IR is applicable to only single resistor, and when several resistors are given, we can obtain one equivalent resistance and apply Ohm's law from total applied voltage. When current of equivalent resistance is obtained, then in series current of equivalent and individual resistance is same, so the current obtained by Ohm's law relation in equivalent circuit can be used as current of all individual resistance connected in series. Let's understand what is parallel connection of resistor. When several resistances in a group are connected in such a way that one end of all resistor is connected together and the second end of all these resistances is also connected together at second position, then this connection of several resistor is called as parallel connection. And in parallel connection, all these resistances would have the same applied voltage. In parallel, voltage remains the same and total circuit current get divides among parallel connected branches. Here in this circuit, three resistors R1, R2 and R3 are connected in parallel, and a source of V voltage is applied across this combination, and the voltage is measured by a voltmeter, and ammeter are used to measure total current and respective branch currents, and the branch current in R1 resistance is I1, in R2 resistor it is I2, and in R3 resistor it is I3. And as per Ohm's law, when applied voltage V is same for all three resistors, I1 is V upon R1, I2 is V upon R2 and I3 is V upon R3. So in this circuit, three resistor R1, R2, R3 are connected in parallel with common voltage V, and respective current are I1 is equal to V upon R1, I2 is V upon R2, and I3 is V upon R3. And as per Kirchhoff's law, at this junction, the incoming current I is equal to sum of outgoing current I1 plus I2 plus I3. And if I substitute the value of I1, I2, I3 in terms of voltage and resistance, then the three value I1 and I2, I3 in terms of voltage and R1 is as, and this voltage is common in parallel connected resistance brought out, then our relation of total current with three resistance is as. So in parallel connected resistor, voltage is the same and the total current get divided among parallel connected resistance branches, and in terms of common voltage, the total current is given by this relation. And if we replace these three parallel connected resistance by an equivalent parallel resistance, then with the same applied voltage across common positions, the total current will pass through this single resistance, and as per Ohm's law, current is V upon R equivalent in parallel circuit. And if we compare the two relation, then in place of total current we can write V upon equivalent parallel resistance, and I1, I2, I3 in terms of R1, R2, R3 are as, and this common V get cancel out from both sides, and we got an relation inverse of parallel connected resistance when summed up will result in inverse of parallel equivalent resistance as given in yellow highlight and blue frame. The solution of next three examples will explain series parallel simplification of resistive circuits very well. Let's take first one. We have to find out equivalent resistance of this given circuit across A and B terminal. So here we can see that at A, the current divides in two branches, and then this divided current again assemble at B point. So across A and B, the voltage of above resistive section and below resistive section is the same, and current is divided among the two. So this upper section of yellow highlight and lower section of green highlight are parallel to each other, and in this yellow highlight, three resistance 1 ohm, 2 ohm and 3 ohm got a common current path, and the total voltage across A and B get divided among these three resistors. So these three resistors 1 ohm, 2 ohm, 3 ohm are in series. So equivalent resistance of yellow highlighted section is summation of three resistance, that is 6 ohm, and in green highlighted part 5 ohm, 4 ohm, 3 ohm got a common current path, and total voltage across A and B get divided among these three resistance. So 5 ohm, 4 ohm, 3 ohm are in series, and their equivalent resistance is sum of individual resistance, and it is 12 ohm. And now we can say in place of three resistance, 1 6 ohm resistance is there between A and B in upper yellow highlight section, and similarly 5 ohm, 4 ohm and 3 ohm are equivalently represented by 12 ohm value, and this 6 ohm and 12 ohm having same voltage across them and current division is there are in parallel. And we know in parallel equivalent conditions, the inverse of equivalent resistance is sum of inverses of individual resistances, and if there are only two resistance R1 and R2 in parallel, and when we take LCM and inverse the relation, we can say that equivalent resistance is equal to product of two resistance divided by sum of two resistances, and the two resistances are 6 ohm and 12 ohm. So the product when divided by sum results in equivalent resistance 4 ohm across A and B terminal. Find out single equivalent resistance between A and B for this given network of 6 resistances. In this yellow highlight section, we have 6 resistances connected in this manner with 0 resistance short circuit at these two positions. If we compare this circuit with previous circuit, we found that this make a great difference in simplification of two circuits. Earlier 1 ohm, 2 ohm, 3 ohm were in series, 5 ohm, 4 ohm, 3 ohm was in series, and the two series combinations are in parallel. But now to simplify this circuit, this short circuit link without any element is treated as point, and similarly this when treated as point, then it looks this 3 ohm and 6 ohm are in parallel to each other. Similarly 2 ohm and 2 ohm become parallel to each other, and 12 ohm and 4 ohm become parallel to each other. So there are three parallel combination of two resistances each, which results in equivalent resistance as product by sum, and 3 and 6 equivalent resistance become 2 ohm, and when two resistors are of identical magnitude, their equivalent obtained by product by sum become half. So half of 2 ohm is 1 ohm. And similarly 12 ohm and 4 ohm in parallel become equivalent resistance product by sum as 3 ohm. And now this 2 ohm, 1 ohm and 3 ohm are in series to each other, and their equivalent resistance is obtained by summation as 6 ohm. So equivalent resistance across A and B of this circuit is 6 ohm. When there exist only two resistors in parallel and the total circuit current is given, then we can find out current in one resistance branch as total current multiplied by second resistance value divided by sum of two resistances value, and we can derive this yellow highlight relation in a very simple manner. The equivalent resistance of two resistance in parallel is given by product by sum, and when the total current passes through equivalent resistance across A and B, the voltage is obtained as total current multiplied by equivalent resistance. And we know in parallel the voltage of R1 and R2 is same as voltage of equivalent. In place of equivalent resistance we can substitute product by sum, and now the current in first resistance is voltage divided by resistance, and the value of resistance R1 get cancel out in the numerator and denominator, and we got expression as total current multiplied by second resistance value divided by sum of two resistance value. And this is very useful relation, but is applicable to only when there exist only two resistors in parallel. Let's understand application of previous relation by this example. We have given a 36 volt source and it is connected to 3 resistor as connected here, and we have to find out current in 3 ohm resistance and total circuit current. Now in these questions of series parallel simplification, it is always advisable to find out first the total circuit current, and to obtain total circuit current we have to find out single equivalent resistance of this combined circuit. And if we study current flow in this circuit, we found that current get divided among 3 ohm and 6 ohm, and it also assembled at second end of 3 ohm and 6 ohm. It means 3 ohm and 6 ohm are parallel to each other, and when this parallel equivalent is represented by a single resistance, then in that single resistance and 4 ohm the current got single path, and the total 36 volt get divided among the two sections. So this single equivalent and 4 ohm are in series. So the parallel equivalent of 3 ohm and 6 ohm obtained by product divided by sum, and this combination is in series with 4 ohm. So series equivalent resistance is sum of two individual resistance. This 3 ohm and 6 ohm parallel equivalent is 2 ohm, and 2 ohm in series with 4 ohm becomes 6 ohm. Now the total circuit got a single individual resistance value 6 ohm, and we can apply Ohm's law. So in equivalent total resistance 6 ohm, the current V upon RT is 36 by 6 ampere, and we know in series the current of equivalent is also the current of individuals. So the total circuit current or current of 4 ohm or reading of this ammeter is 6 ampere, and now this total current will divide among the two parallel connected resistance 3 ohm and 6 ohm, and we can find out current in 3 ohm as total current multiplied by second resistance 6 ohm divided by sum of 2. Here total current is 6 ampere obtained by Ohm's law calculation on single equivalent resistance 6 ohm, and for 3 ohm current calculation the other resistance parallel to 3 ohm is 6 ohm, and the sum of two resistance connected in parallel is 3 and 6 9, and when we simplify the current in 3 ohm comes as 4 ampere, and if similar type of calculation is done for 6 ohm then we will find the current 2 ampere. So here total current 6 ampere get divided as 4 ampere in 3 ohm and 2 ampere in 6 ohm. In last 13 minutes we have studied single resistance value of series connected resistances as well as single equivalent resistance for parallel connected resistors, and we have also studied how simple series parallel circuits are solved. Our other learning video of the same playlist are equally useful, and if you find them useful, do share it with your friends. Happy learning. Thank you very much.